In this practice problem, you see several of the Lewis structures, A and C, that we saw in the last set. But we're going to go a little bit deeper to understand why one may be better or worse than another. So sulfur dioxide, SO2, could be drawn like this and drawn like that. We talked about how those are exactly equivalent to one another, and formal charge is a way to support and explain that. We do need to remember that formal charge is kind of made up. It's not polarity. It's not really how atoms are sharing electrons, but it's our way of keeping track of electrons to see which thing's the most likely to happen. It accounts for Zeph, it accounts for protons, energy levels, and valence electrons. So when we think about an oxygen atom, for example, it's got a Zeph of +6, and it's got 6 valence electrons. When it's got 6 and 6, it perfectly cancels one another out and maximizes that kind of attractive ability. When it's got extra electrons, because the Zeph is fairly high, it does pull those in, but it has more electrons than it had the Zeph to cancel it. So when we look at a Lewis structure, we are looking at the electrons that it has as lone pairs. Those are its own electrons, but we also split any bond in half to say that those kind of or half of them belong to that oxygen. Obviously, from a covalent bonding sense, it is sharing both of those to complete the octet. But this oxygen brought 6 electrons, and it has 6 of its own electrons plus 1 around it. It's as if it has 1 more electron than what it brought, or the electrons around it are more than the Zeph. That's what a formal charge of -1 means. It's got more negative than it can balance out. The sulfur brought 6 electrons, has a Zeph of 6, but it only has 5 of its own electrons. 1, 2, 3, 4, 5, half of each bond. So it's as if it has a little bit more positive charge. The oxygen over here is a perfect balance of 6 and 6. We said that this other drawing in the previous one was exactly balanced with it. And that's true. A -1 on an oxygen, a +1 on a sulfur, a 0. The formal charges add up and cancel to 0, which is good because the molecule has a charge of 0. In this and this, we'll see something that'll be in the next video, that some elements, the larger ones in rows 3 through 7, can actually expand their octet to have beyond 8 electrons. Sulfur can be full and stable with 8, but it could hold 10 or even 12 in some compounds when that makes it more stable, or when that fills the energy levels or the octets a little bit better. When we do this drawing, the oxygen has 8, but there's 6 of its own. This oxygen also has 8, but it also gives sulfur access to more electrons. 1, 2, 3, 4, 5, 6. So both oxygens have a formal charge of 0, as well as the sulfur. The most favorable of these structures is this one right here, 0, 0, 0, because everything is balanced with its formal charge. Sometimes you are given multiple Lewis structures and asked which one's better in formal charge. Sometimes you're asked to draw multiple Lewis structures and then use formal charge. So it's important to be able to assign this and kind of also think outside the box in terms of some of those other ways we could draw a compound by expanding octets for our larger central atoms. Sulfate is another example of that. Sulfate is SO4. When we first draw SO4, when we follow the 5 rules as they're written, we would connect everything with a single bond. We'd fill with 6 dots all around. And this would be a really good, in fact, perfect drawing for that. The problem with this is that each of the oxygens has an extra electron on it for a formal charge of -1, and the sulfur only has 4 of its own electrons. So we've got -1s and +2s. But the formal charge does add up. We've got -4, +2, so it gets to my -2 charge for my sulfate ion. It does work out. But if I start to expand sulfur's octet, we could see that by putting a double bond in one place, that the oxygen actually goes to a 0 as a formal charge. and we see it here, here, we'll see it here and there. Oxygen with 2 lone pairs and either a double bond or 2 single bonds has a formal charge of 0. With its 6 electrons, it often forms 2 bonds in its most likely arrangement. The halogens often form 1. Nitrogen often forms 3, and that helps us to know and predict what structures there would be. But when we have a polyatomic ion, our formal charges have to add up to its charge. So when we go to this next version of sulfate, which is the most likely or most favorable version of it, we still do have to have some negative charges. Those negative charges end up here on 2 of the oxygens, whereas the oxygens and the sulfur are zeros. We could add another double bond on the oxygens. I didn't include any beyond this. But you could have 3 double bonds in a single or 4 double bonds and no singles. And in that case, our oxygens would all end up as 0, but our sulfur would end up ultimately as the negative thing. We want the negative charge when we have to have one, and we would need to have one here in this polyatomic ion, to be on something with a higher electronegativity. So fluorine, chlorine, oxygen, and nitrogen are the ones likely to have a negative charge in a polyatomic ion. Here on C, we talked about acetic acid. This and this both follow the rules, but oxygen wants to have 2 bonds and 4 dots. So in this case, we've got 2 bonds and 4 dots on this oxygen and on this oxygen. But over here, the 6 dots with a single bond give that oxygen a -1 formal charge. The 2 bonds here and 1 bond there, that's 3 bonds with only 2 dots. That oxygen actually has fewer electrons than it brought or than it wants. Although, according to the rules of a Lewis structure, both of these are fine. They are not equivalent because the formal charge here is better than that. That means this is the correct molecule and this one is not. So not all different pictures are created equal, and that means resonance doesn't really exist equally between these two. This one is much more dominant or much more likely. And in fact, we may not see this one at all, or that one would not be counted correct as a drawing. For OCN-, that's a polyatomic ion, so we do have to have a negative charge. We've got a couple different arrangements here. Our least electronegative element is almost always in the middle, carbon. We could draw several more of these with oxygen or nitrogen in the middle, but if we know ahead of time carbon's going to be in the middle, because it's the least electronegative, we save ourselves some time. This arrangement here uses the electrons that we have, which is 6 plus 5 plus 4 plus 1. That is 16. We have 16 electrons. Everything has a complete octet. Oxygen has the 2 lone pairs and 2 bonds. Carbon has 4 bonds, which makes sense to share its 4 electrons. Nitrogen has the same arrangement here as oxygen, so it actually has 1 more electron than it brought. Here, the oxygen has more bonds and fewer dots. The nitrogen has more dots and fewer bonds. Our formal charges get more extreme. Nitrogen becomes more negative, with oxygen becoming more positive. This other arrangement is the most favorable. So that guy at the bottom is the winner. These two look similar. We've got 0, 0, and -1. And this one, honestly, the first top left one looks the best because everything's nice and balanced if we just kind of think of it from that perspective. But we have to have a negative charge. So the negative charge is going to be on the element with the highest Zeph, or the element that can attract the electrons the best. Oxygen has a higher electronegativity and a higher Zeph than nitrogen. So since we have to have a negative charge, it goes on to oxygen. This is the most favorable structure. Although there may be some actual resonance from this one right there, we may see a little bit back and forth, but this one's definitely dominant and favored.